So today all right. So today I would like to, first of all, I would like to thank the organizer, NANOCAT, for inviting me as one of the NANOCAT webinar series for today. So today I will share my presentations on the graphene for electrochemical sensor. So first of all, I want to check my mic. Is it clear, Dr. Chi?
Yes, clear.
Okay, so I will proceed. So without further ado, I will share my presentations overview. Okay, first I will introduce the discovery of graphene and also the introduction to the electrochemical sensor, advantages and applications of the electrochemical sensor, and we will see the example for the synthesis of graphene-based nanocomposite and the introductions or basic of the electrochemical sensing technique. And also I will introduce some example for hybridizations of graphene-based nanocomposite for the electrochemical sensor applications. So conclusion and also the references. So before we understand more about the graphene-based nanocomposite, let's first talk about graphenes. So what is graphene? Graphene is actually a single layer or monolayer of carbon atom that tightly bound in a hexagonal lattice structure, and it is a single layer of a graphite. If we take out a single layer of a graphite, so it can form graphene. So basically, it is nothing else than just a single layer of a graphite. Okay, the introduction, a bit introductions about the graphite. So graphite is actually a pure crystallite carbon that was discovered in 1564 in the Citaville, England. And at the first time, it was used by a farmer to mark their sheep. And later on, in 17th centuries, it was sewn into a sheet and then cut into a square rod. Later on, insert into a handcuff, a wooden holder to create a pencil. So as you can see from the figure here, is a comparison between the 70th centuries of the pencil, and this is nowadays pencil. Okay. Okay, now let's look how graphene has been discovered. It was first discovered in 2004 by two Russian physicists, Professor Andrei and his student at that time, Professor Konstantin Neveselov at the University of Manchester, by using the exfoliation method using Scotch tape. So they are exfoliated graphite by using the Scotch tape to produce graphene. And in 2010, they have received the Nobel Prize in Physics because of this finding for breaking a groundbreaking experiment regarding the two dimensions material of graphene. So there is a few structures of graphene. It can be rolled into 0 dimensions to form fluorines, and also can be it can be wrapped up to form a 0 dimension of fluorines, and it can be rolled into 1 dimension to form carbon nanotubes. And for the 2D, 2 dimension, it can form graphene sheets, and as it stack up, it can form 3D graphite or 3D diamond structure. So why people or researchers are looking for the graphene or work on the graphene? It is because it has the amazing properties of the graphene. So graphene is the thinnest known material, and it only one atom thick. It's about almost 0.34 nanometer, and it will take about 3 million stack of graphene sheets to be equal to a width of pencil tip. And despite of being the lightest known material, it also the strongest material ever measured, which is 200 times stronger than a steel. And the source from Wikipedia has given that idea is require an elephant that balance on the pencil to break through a sheets of graphene with a thickness of clinch films. So it's estimated the pressure is about 130 gigapascal. Furthermore, graphene also sheets that allow nothing to pass through it except the water, because the molecule of the water is about 0.27 nanometer. Therefore, it has a huge potential to turning the ocean into a vast drinking supply, as it is possible to remove salt from the seawater. So last but not least, it also can conduct electricity and heat better than other material. Okay, now let's look how graphene can be synthesized from the graphite. So there is two approach, namely bottom up approach and also top down approach. There are 6 significant major methods that has commonly used, which is epithelial growth, chemical vapor deposition, PECVD, chemical for the top down is a mechanical cleavage, chemical reductions of graphene oxide, chemical oxidation, and also electrochemical treatments in order to produce, has been employed in order to produce a graphene from the graphite. So let's look at to the potential of the graphene. There are various potential application of the graphene, including the ultra speed transistor, and also has been used for the fabrication in the sensor, also fabricated as a superconductor and also battery technologies, and it's currently being expanded into automotive and also aerospace material. It also used for the conductive ink, paint, and also 3D printing, and last but not least in sport equipment, and also combined with the rubber and also plastic in order to improve the properties of the material itself. Actually, I cannot move myself. Okay, now. Okay, let's let's look at the introductions for the electrochemical methods. So the growing in the various of the biosensor has increased because of the demand on healthcare applications activity, such as monitoring for the pressure, blood pressure, for example, and monitoring for the DNA, and also what intruders in our body also can be determined by using electrochemical method of biosensor. So during past 15 years, there are various techniques has been developed for the sensing, such as atomic absorbance spectrometry, capillary electrophoresis, micro X-ray fluorescence, spectrometry, chemiluminescence, and many more. So, however, these analytical methods usually require an expensive equipment, and also it's require the tedious detection procedure, and also need an experts to handle the process, and also often time consuming. Particularly, it is but difficult to handle. So in light to this development factor, the electrochemical approach is the most promising candidate due to their simplicity, high sensitivity, highly specific. It also user-friendly and reliable technique. Other than that, there is another benefit of electrochemical sensor, such as it is can be just used for cell fabrications, It's affordable, simple, and it also can be used for a real-time analysis. So let's look at on the electrochemical histories of electrochemical sensor. Okay, in 1906, it was the first development of the glass electrode by Kramer, and 3 years later, the introductions of Haber electrode was introduced by Haber and Clemenceau, and then the first introductions of the amperometric sensor was introduced by Professor Leland Clark, where he introduced the glucose biosensor, and the first and the most widely used commercial biosensor in 1962 by detections of the glucose in the blood. So this is the mechanism that we use. All right. So principle for the electrochemical sensor, the electrochemical sensor is actually a device, a small device that used to measure the physical quantity of an analyte in a sample matrix. So the response will be continuous or reversible. So it will consist of 3 electrodes, the reference electrodes, and also the auxiliary electrode. Normally we are using platinum wire, and the working electrodes. So the working electrode is there where we are covered the transducent with the transducent element that known as recognition layer. And this recognition layer may be the chemicals and also biological. Therefore, this recognition layer will interact with the target analyte. So these 3 electrodes will connect it into potentiostat, where the transduction element will translate all the chemical changes into the electrical signal, where we can see the productions of the graph due to the electrical signal change due to the concentrations of the analyte added into the solution. So the electrochemistry that involved will be the oxidations or reductions. So as I mentioned earlier, the analyte will be detected with this transducer layer to produce a product, is either oxidations or reductions. And then the signal, the chemical signal, will be changed into the electrical signal to form the various of the analytical graph techniques, such as this is a cyclic voltammetry, Nyquist plot, and also the chronoamperometry. So these signals are related to the analyte concentration. So there are various electrochemical sensor applications. It can be used for environmental monitoring for oxygen sensor, nitric oxide, and also hydrogen gas, and many more. And for the biomedical application, it can be used for glucose sensor, in vivo and in vitro application, diagnose and treatment for the disease and cancer, and also DNA immunosensor. And for the pollution, can be used to detect or to determine the contamination. For example, hazardous waste, hydrogen peroxide, and nitrite, toxic metals, and formaldehyde that appear in the wastewater. Or all right, and it also can be used for biological technologies to monitor the nutrition analysis and also biomolecule in the product. Okay, let's look at to the how this is an example of synthesis, how graphene-based nanocomposite can be synthesized for the electrochemical sensor. Can I minimize this? Okay, let you look at to the how significant graphene to be used for the, okay. Okay, so the electrochemical sensor applications can be used for various applications such as in the environmental monitoring, for example, oxygen sensor, nitric oxide detections, and also can be used for biomedical applications such as to measure the glucose in vivo and in vitro application, diagnose of the treatment such as disease and cancer cells, and DNA sensor, immunosensor. And it also can be used for monitoring the pollution or contamination that appear in the wastewater or in the drinking water, such as hazardous waste, hydrogen peroxide, nitrites, even toxic metal and formaldehyde. And also can be used in biotechnology and food industry to monitor the biomolecular sensor, nutrition analysis, to measure the food moisture analysis, and also in drinking water purification. Okay, now I will share with you a few example or synthesis of graphene-based nanocomposite for electrochemical sensor. Okay, first of all, we look at on the significance of using graphene as a graphene-based electrochemical sensor. So graphene has a wide electrochemical potential window and also has a low charge resistance due to the thickness of the atomic thickness, and also well-defined redox peaks with the excellent chemical stability in various and electrolyte, and also exhibit very high enzyme loading because of the high surface area to volume ratio. And then due to the structure of two dimension, it can make it more efficient in detecting absorbed molecules. And also, last but not least, it has the significance for a more uniform distribution because of the presence of active site. However, the main challenge of using only graphene as a base for electrochemical sensor is that it produces very large noise that lead to the low signal to the noise ratio. So in order to enlight these issues, we introduce nanomaterial hybridized with the graphene in order to perform the electrochemical sensor. And these nanomaterial example is that metal nanoparticle, metal oxide nanoparticles, and also carbon materials. So why introduction of this nanomaterial can enhance or overcome the problem earlier? This because nanomaterial can immobilize the biomolecule. It also can enhance the catalytic of the electrochemical reaction to become more sensitive, and it also can enhance the electron transfer due to the size of nanomaterial or nanostructure, and also can label the biomolecule, and also can act as the reactant due to the high surface energy. So let's look at to the how we can produce the nanostructured material. So there are two approaches that can be used to produce nanostructured material. The first one is top down and also bottom up approach, where we are using, for the top down, we are using the bulk material, and then we divide it into a fragment to form a nanostructures, and for the bottom up, we can form it from the ions or atoms to form a cluster, and finally to form nanostructured material. So top down, we have a few technique or few methods that can be used. Is among them is chemical etching, laser ablation, lithography, thermal decompositions, and also sputtering. And for the bottom up, we have to approach. And also, green synthesis also can be done for this bottom up in order to produce the nanostructure. Other than that, it can be bottom up approach is the chemical vapor deposition, salt gel, and also somehow we are using hydrothermal as well, spray methods, molecular condensations, and also aerosol processes. Okay, for the electrochemical technique, there are a few methods or technique for analytical measurement. Among of them that we are always use when we are dealing with the electrochemical in the potential state. The first one is the linear swept voltammetry, or known as LSV. And there is the second one is cyclic voltammetry. And also the third one is differential pulse voltammetry, DPV. This one. And also the square wave voltammetry. And last is the amperometry, where it measure currents towards the currents with the function of time. Okay, let's see some example for the hybridizations of graphene-based nanocomposite for the electrochemical sensor. Okay, this is one of the example when we are producing a myoglobin gold nanorod reduced graphene oxide nanohybrid for detection of nitric oxide. So for the preparation process, reduced graphene oxide has been combined with the gold nanorod by using seed growth method, and then also combined together with the myoglobin under simple sonication methods. And finally, we obtain the nano hybridization, and this has been used for detections of nitric oxide. Okay, so it is well known that the sodium nitrite can be served as the source of nitric oxide in the acidic source, which is with the pH less than 4. So it will undergo the proportion reactions to produce nitric oxide ion, and then with the addition of the sodium nitrite in the bulk electrolyte, so we can generate the series of the nitric oxide. So here is the cyclic voltammetry, and you can see that as a compared with the bare GCE, the nano hybrid showing the higher current of detection nitric oxide. So here is a comparison with the other modified electrodes, such as only for gold nanorod, reduced graphene oxide only, and also only for myoglobin. So as we compare with those modified electrode, the nano hybrid show the highest peak in current. So in addition, we are using the LSV with the addition of sodium nitrite of 10 micromolar up to additions of 100 micromolar. And from this regression graph, we can calculate the limit of detections to be 5.5 micromolar. So for the selectivity, we also can test, or we can study the selectivity by using the linear swept voltammetry. Okay, in the introduction or in the presence of various interference here, and also the electrolyte ions such as KCl, NAF. So as you can see from this LSV, there is only peak appear for the detection of nitric oxide. Other than that, we cannot see the appearance of peak. Okay, and then there is a second example preparation of Graphene-nafion hybrid for detection of nitric oxide as well. So we are using, this is the hydrothermal method to hybridize graphene oxide and the nafion. And then later on, we are using this modified electrode to detect the nitric oxide. So again, you can see from the CV here, the hybrid Graphene-nafion showing the highest detection in current for nitric oxide. Okay, and then we are using the square wave photometry to calculate the limit of detection. Right, from the linear graph here, we can calculate the limit of detection due to the increment of concentration of nitric oxide from 50 micromolar to 10 millimolar. So the limit of detection was calculated to 11.61 micromolar. We also study the selectivity, okay, with the presence of ascorbic acid, dopamine, and nitric oxide. So you can see that there is a separate, we can see the very clear separation for those elements. So here represent the ascorbic acid and here is the dopamine. Whereas for the nitric oxide, it shows the high or significant peak for the current. Okay, this is the third one, the preparation of flower-like zinc oxide nanocomposite, zinc oxide reduced functionalized graphene oxide nanocomposite for detection of nitride. So we are using the hydrothermal method to produce flower-like zinc oxide reduced functionalized graphene nanocomposite. So there is a clear picture here where the FSM image showing the flower shape of the zinc oxide that anchor on the both sides of the reduced functionalized graphene sheets. Okay, here is in the front and there is another at the back. So for the analytical electrochemical analysis, we study by using CV and also LSV. Again, we introduce the sodium nitrite to form the nitride. And then, as you can see from this figure, it's showing the higher current as compared to other modified electrodes. Okay, and then in additions of the nitric oxide from 0.1 millimolar to up to 3 millimolar, we can calculate the linear graph and also finally limit of detection, which is 33 micromolar. Okay. And then to study the kinetic of the material, we also can use the amperometric, which is current versus time curve, where we can determine the step of the introduction 10 micromolar of sodium ion, and then also we can study the interference study by introductions of this one metal ion interference and also the electroactive compounds such as uric acid, glucose, ascorbic acid, dopamine, and hydrogen peroxide. So you can see that there is no changes, obviously, observed in this, even though we are introduce the interference. But when we introduce the sodium nitrite, so nitrite to form the nitrite, we can see that there is the changes start to increasing, and also for this one. So we also determine this nitrite in the various sample, such as river water, lake water, sea water, and tap water. So we can see that the percentage of recovery is shown here. Okay, there is another example of preparation gold nanorod coated reduced graphene oxide for the electrochemical sensoring detection of NADH. Okay, so the preparation has been for this gold coated reduced graphene oxide. We are using a simple sonication methods, and then we fabricate in the modified electrodes to study the oxidation of NADH to NAD ion. So again, this is cyclic voltammetry. We can see that the difference of a bare GCE and then the modified electrodes. So it shows the higher in current for detection of oxidation of NADH. So FSM image here showing the A figure shows only for the reduced graphene oxide, and this is for gold nanorod. After fabrication, we can see that there is a lot of gold nanorod has been coated on the reduced graphene oxide sheet. Okay, with the width of gold nanorod, with the width of 13 nanometer, and also the length up to 44 nanometer. Okay, so for the amperometric response, we introduce 1 micromolar of NADH, right, and then up to 31 micromolar. So from the linear graph, we can calculate the limit of detections to be 0.22 micromolar. So it shows the lowest detection limit among as compared to the previous study by using graphene as the base, or graphene-based nanocomposite. So our study showing the lowest limit of detection. We also study the interference. So we can see that introduction of NADH can obviously shows the separation even at a higher concentration. So ABC showing increment in the interference concentration, okay, of ascorbic acid and dopamine. But for NADH, it shows, you can see from figure here, it shows very significant separate peak compared to the others. Okay, so it is possible for a real-time sample because of this anodic peak, and also can be well separated even though in the presence of many interference. Okay, this is another one, the preparation of nanosize of Graphene-nafion for detecting dopamine. Just now I'm showing the same modification method to detect the nitric oxide, but this one also can be possible to detecting of dopamine. So square wave voltammetry here, okay, showing that the hybridization of Graphene-nafion that can be used to detect the dopamine concentration from 300 nanomolar up to 50 nanomolar. So we can see that from the calibration plot, we can calculate the limit of detection. So the limit of detection for that technique, SWV technique, is 166 nanomolar. So here is the interference study. So we can see that there is a well separated peak for ascorbic acid, dopamine, and also uric acid. This method is using the linear swept voltammetry curve. Okay, this is another example has been prepared by my previous colleague. showing the preparation of reduced graphene oxide, titanium oxide, to detect the dopamine by using isothermal method. So as you can see, this SWV can shows that the detection limit up to 6 micromolar over the linear range of 2 to 60 micromolar. This is a bit different from mine because he using the isothermal method, whereas my previous method is hydrothermal. Okay, other than that, graphene-based nanocomposite also can be used to detect the mercury ion detections. So as this one, example is the preparation of titanium dioxide decorated on reduced graphene oxide nanocomposite for mercury ion detection. So this method, in this method, we are using hydrothermal when introductions of graphene oxide, titanium isoproposite, and also TETA as the reducing agent, and also the to isolate the distribution of titanium on the reduced graphene oxide sheet. So as you can see from the TEM image here, there is a distribution of TiO2 on the graphene sheet. So there has been prepared by 3 various temperature, 120, 150, and also 180. So among of these, 120 showing the better detections of mercury ion. As you can see from this figure F here, there is 2 peak appear, which is reductions at peak here, negative 0.2 volt and then 0.4 volt, okay, for reduction of mercury ion, represented by these 2 peaks. With the higher in current as compared to the other, this one is for 100-degree temperature, lesser current, but for 120-degree temperature, showing the highest current, reduction current. Okay, as for the novelty, for this finding, so one-step hydrothermal method is most simple and versatile method to produce the functionalized graphene-based nanocomposite that can be used for application in various electrochemical sensor to detect many, to detect chemical analyte and also metal, heavy metal, or etc. And then it also reliable test that can has potential for real sample analysis because it hold promising in the direct analysis of the environmental sample. And then the immobilization of myoglobin with the gold nanorod and also reduced graphene oxide, okay, which means introductions of nanomaterial can amplify the detection signal and improve the electron transduction, and also can reduce the detection limit in the electrochemical sensor. So modified electron, highly selective also towards the determination of selected analyte, even in the presence of various potential interference species. Okay, as a conclusion, okay, since 2020, because of the high demands has been given to the flexible electronic product in the market, so the demands will be keep increasing. So the efforts towards the improvement for the stability and reliability of sensing nanomaterial, it's required in order to be used for real application. And also the sensor integration, integrated system by combining with the micro controller unit for the communication, energy, temper handling also need to be developed. in order to fulfill the specific needs. And in order to achieve this, we need to have a collaborative research to essentially to achieve this goal, which means we have to need to have a collaboration among the person or researcher in the material and devices, and also in engineer for the software, and also integrate it into circuit, and then also researcher or person in the medical field in order to achieve this success. So here is the reference that has been used for this presentation today. So therefore, I end my presentation. Thank you very much.
Thank you very much, Dr. Marlinda, for your kind webinar, the presentation. Indeed, this is a very interesting research about graphene. Open to the floor if you have any questions to Dr. Marlinda. Before that, I would like to request participants to kindly fill in the survey form available in the chat box. Kindly click on the link to the Google survey form. Thank you. If you have questions to Dr. Marlinda, please feel free to ask Dr. Marlinda. Due to the limitation, we have about 10 minutes left for this webinar section because our version is personal. Our Zoom version is personal version. We are yet to subscribe the enterprise version. Thank you. Yeah, maybe I start a question first to Dr. Marlinda. Dr. Marlinda, my question is regarding the graphene and graphene material, and how secure is this material being coated onto the surface of the electrode?
Okay, all right. So, all right. Okay, for this, is actually we also having the difficulty at the first time because it tends to leaching from the GCE, right? If we coat it, it tend to leach when it's swollen in the electrolyte. So we have to secure it. We has one approach that we are using where we are coated with the polymer, conductive polymer on top of it. For example, we can use PMMA or also Nafion. So we just coated a very thin layer on that after you coated your modified sample, and then after it dry, and then we coated with the polymer, conductive polymer. It will not interfere much on the analytical measurement.
I see. So the polymer will glue onto the surface of the
correct.
electrode.
Yes,
I see.
It will secure.
I see. Is there any questions from the floor? If you have, please direct to Dr. Marlinda.
I think there is one question. How good is the reproducibility of the sensor? Okay, so we of course we also measure the reproducibility of the sensor. We have produced 55 sample with the 50 cycle. So each new batch that we coated, we run for the cyclic voltammetry for more than 50 cycles. So then we calculate the we call it SDV, the average. So it's less than 3%. So it's quite reproducibility, and also showing the same value every time we reproduce it. Thank you, Azman.
Dr. Azman.
Dr. Azman, sorry. Okay. Thank you, Dr. Azman.
Yeah.
May I know how can we prove that the material developed is nanomaterial? Is DM service available? Okay, So yes, you can because we not just only for this, we not just only after we prepare the material, we directly fabricate on the GCE or the modified electrode. We need to do some confirmation such as XRD, because we are producing, we also dry it and then produce it in the powder form. So we test for SRD, we test for the XPS, and also UVVs. If in the solution form, we can test for the UVVs and TEM, so we can confirm this nanomaterial in terms of their size and also in terms of their elements as well. Thank you. I cannot read the name. Okay, thank you.
Okay, we have about 5 minutes left. If you have questions, please take this opportunity to ask Dr. Marlinda.
No, how do what's that? Mr. Salahuddin. Okay. Mr. Salahuddin. Dr. Salahuddin. Okay, can I know how dopamine interact with the nanocomposite mechanism? Okay. All right. So dopamine is actually one of the enzyme that has important role for the human nervous or hormonal system, for cardiovascular system. So it's actually swollen in the when in the electrolyte, and then we can determine the different oxidation peak that appear for the dopamine. So maybe you also can refer to the to my publication that shows more details on this as well. Okay, I will share if you are if you want to see more about that. I will share with you the how the mechanism for that interaction.
Thank
Okay,
you.
I will share.
Yeah.
Okay, I will share my email here. If you have more questions, you can ask me through my email.
Yes. Dr. Marlinda, we can see your email address here.
Oh, see, I showed already.
It's on the slide. Yeah.
Okay. Yes, in my slide.
We have about 3 minutes left. Yeah. Please take this opportunity to the rest of the audience. All right, if you have no question to Dr. Marlinda, please join me to thank Dr. Marlinda for her presentation today. Thank you very much.
Welcome. Okay, thank you.
Yeah, we still have left. If you have questions.
Oh, we have 2 more minutes.
Yes.
Okay, I saw one chat here. Oh, no. Okay. I'm also would like to take this opportunity to what if you have like you would need a collaboration or in terms of doing collaboration, I would like to work with you guys as well. If you have any suggestions or interesting in any other nanomaterial to combine with the graphene in order for purposes in electrochemical sensing application for other analyte, not just what I mentioned here. So I welcome all those research as well. So you may contact me through my email.
Thank you, Dr. Marlinda.
Okay, all right. Okay.
So we see no further question from the chat box. And we have 1 minute left. So if no question from now, I will end the section anytime from now. We have less than 1 minute.